my turn is now, and let me tell you that this is something, quotes, ambitious. Sorry. Why ambitious? Because, honestly, I didn't think about that before 10 years ago. This is the product of the last 10 years of papers, mathematical thought, and so on. Anyway, my background is mathematical physics, and so I love mathematics. And the easiest thing that you can study in mathematics is a straight line. There is nothing easier than that. And this is the straight line. So let me tell you the same story, but with the words of biologists. So they call molecular clock in very loose terms. Of course, I'm not using the rigorous terms. But basically, with an example, you understand the notion. For instance, consider two species, horses and humans. Pick up the DNA of horses, check that against the DNA of humans. The vast majority of the two DNAs are pretty similar, but there are differences. Meaning that in the, roughly speaking, 30 million years that have elapsed since the two lineages diverged, changes occurred in the two molecules, okay? Now, the great discovery, sorry, that's it. The great discovery that was made 50 years ago by these two gentlemen, Emil Zuckerkandel, I'm using the German pronunciation because he was from Austria, and Linus Pauling, of course, the famous Nobel laureate twice and so on, is that they realized that this molecular clock, that is, this property that if you pick up two lineages, the number of differences in between the two DNA molecules is proportional, this is the key word, proportional to the amount of time elapsed since the two lineages diverged. This is a general law of nature. And after 50 years, we are so confident, I mean, the biologists are so confident about that they invert the reasoning. Meaning that if they discover a new species, and of course check the DNA of that with the DNA of another species, they infer how long ago the two lineages diverged, okay? So this is a law of nature. Now, the same story, but stressed in a mathematical sense. So let me go back, please, just to make it clear. The key point in the story is the word proportional. Proportional means a straight line in a diagram where on the horizontal axis you have the time, on the vertical axis you have something else, but the important point is that the plot is a straight line. This is the key point, okay? Good. Now, let me mention other things. There has been a great debate in the biological and molecular biological world when this gentleman from Japan, Moto O Kimura, put forward his neutral theory of molecular evolution about 1968, but it took quite a bit of time before it was realized mathematically what he was talking. He was writing very mathematical papers. The idea is very simple, that at the molecular level, not at our level, but at the molecular level, practically there is no Darwinian selections. That is, what we learned from Darwin, that you know the better species prevails over the worse species, does not work for molecules. Molecules obey the law of quantum physics, not the Darwinian selection stuff. In plain terms, this is the meaning. So I was fascinated by these two facts, which are basically the same fact, if you want. And I tried to build up a mathematical model that derives the existence of the molecular clock from the first principles of the theory. So let me please point out, it's very non-modest, and I do apologize about that, but I had to make a comparison with Kepler and Newton, so that you realize historically the story is pretty much the same, of course, about the different subjects. Kepler was a great astronomer. He took the data of Tycho Brahe, converted that into a number of calculations, and discovered the law of motions of the planets around the sun. First, second, and third law. Great. But Newton, in my opinion, did better, because Newton was able to prove mathematically, no observation, mathematically, that the three laws of Kepler are just the mathematical consequences of a single superior equation, which is the law of gravitation. Now, by doing this, Newton really made a huge step ahead, because he established a new branch of science that used to be called celestial mechanics in the 1700s, in the 1800s, and today is called astrodynamics. But essentially, in plain terms, is the calculation of orbits just on mathematical basis. Today, we have such a perfect knowledge of the orbits of all kinds. I come from the space world, so I can guarantee that we certainly will never put up a space mission to check whether the calculations are correct or not. We know them in advance that the calculations are correct, period. So what I have been trying to do here, it's very ambitious, and I apologize about it, but this is the attempt, is to derive a theory such that the molecular clock is a consequence of the theory, is a mathematical consequence of the theory. Now, let me just tell you quickly what is the idea. The idea is to use a stochastic process that is a random function, like the one shown here, that is called geometric Brownian motion, and has the particular capability of having an exponential mean value. So you see the horizontal axis is, of course, the time. We have two different realizations according to the values of the two different parameters in the stochastic process that are called mu and sigma for historic reason, because practically the log-normal distribution is the exponential of the Gaussian distribution. Of course, I'm talking very loosely. I would never be allowed to say so in a university course. They would throw me out. But basically, this is the idea. You start with the Gaussian, and then you put E, the number E, 2.7, whatever, raised to the Gaussian, and that is log-normal. This, in plain words, is the idea. Now, geometric Brownian motion has, as I mentioned, this peculiar property of having an exponential increase in mean value. And this matches very well with what we know happened over the last 3.5, 4 billion years, what you please, on Earth. If you make a plot where on the horizontal axis you have the time, and on the vertical axis you have the number of living species. This is just the same story for over the last billion years, but you see obviously what the exponential tendency is. I won't say the calculation, but essentially the first line means just that. The mean value of the L, capital L means log-normal stochastic process, is an exponential. E raised to a coefficient b or sigma, as the b is actually what in other books is called sigma square over 2, times t minus ts. Now, ts stands for time of start. Of start of what? Of start of life on Earth. So, contrary to the ordinary statistics course where they teach you the log-normal distribution, but they assume, quotes, for simplicity, that it starts from 0. Now, this is a stupid simplicity because it obscures the fact that you can shift the time axis as you please, and so you can let it start at any time you please, which is what happened over the Earth in time when a new species arose, and you use that for a log-normal distribution. So this is the idea. I had to give a name. Sorry, I call that a b-LOGNORMAL, meaning a log-normal starting at time b, birth. B-LOGNORMAL means that. A b-LOGNORMAL is a probability density in the time, not in whatever you want, as usually happens in statistics. So this is the shape. This is the ordinary log-normal, so it starts from 0. But of course, this is the equation. As I mentioned, the leitmotif is e to the Gaussian equals the log-normal. And this is the equation of the b-LOGNORMAL, that is log-normal starting at time b. It's a little more complicated, but there is nothing special. The normalization condition is, of course, that the integral from b, the birth, to infinity equals 1, and this is indeed the case. Now, just a few words about the peak of this thing. These are the equation of the peaks. And I was lucky, really lucky, because checking the first two equations that give you respectively small p, the abscissa of the peak, and second equation, capital P, the ordinate, I came to realize what is written in the second line. Inverting the first equation, you get the log of p minus b equals mu minus sigma square, and mu is given by that. Now, the point is that the equation in P, capital P, may not be solved for sigma, but you can separate these two equations and you get what I call the peak locus theorem. It's a theorem. This is in the easiest version where the rising curve, like the species curve, is an exponential. But actually, thinking about that for 2 or 3 years, I was able to generalize that to all cases where the upper curve is not an exponential. It could be whatever you want. So this is an important generalization. Incidentally, I did all the calculation by virtue of the NASA symbolic manipulator maxima, because honestly, I wouldn't have been able to do all this integral by hand without making errors. But NASA, 50 years ago at the time of the Apollo flights, wrote this fantastic code called Maxima that you can download for free, which is why the students and the readers of my book love it, because they just download it and they do whatever they please, right? So I use that. I don't give you more details, but this is the point. Now, one more result. We now have to step into another field of science. So far it was a statistic, probability, whatever, but now we go over to another important field of today's science, information theory. Information theory started in 1948 with the famous papers by Shannon, Claude Shannon, who was trying to figure out mathematically the capacity of the telegraph line. In plain words, at the time, of course, people were using telegraphs. So I was wondering how much information, not energy, information you could put into an information channel, and there is a maximum value that he was able to compute. And so in doing so, he invented a new definition of entropy. There is a story. He didn't know how to call this new definition, and that is the upper line for the b-LOGNORMAL. So he went to the famous mathematician, the mathematician in Princeton. Okay, yeah? Von Neumann, sorry, von Neumann. So he went to von Neumann and said, okay, here is my equation. What do you suggest I should call them? And von Neumann had a humor in his mind, and so he said, call them entropy, because nobody knows what the hell entropy is. No? So you will always be safe by calling it entropy. And this is how the Shannon entropy came into the literature. But actually, it's a wonderful discovery, because you can compute the entropy for any probability distribution, which was not the case with the previous entropy, which was the Clausius entropy of physics, going back 100 years earlier. So you can compute the entropy of b-LOGNORMAL, and that is the result. Now, that is essential for my theory, because I claim mathematically that life is a b-LOGNORMAL. So you have a starting point, which is called birth, then you have a climbing up to adolescence, that is puberty, then you have a further climbing to you reach the peak, mature, the best time in your life, and then you decline. At the decreasing part, at the senility, you just draw a straight line that touches the axis, and finally the touching point is death. This is my mathematical definition of life. Otherwise, I cannot derive any theorem, of course. Now, if you assume that and you dig a little more, but the calculations are really trivial, you know, a freshman or sophomore would be certainly able to do them. You discover these two things. That is, I call them history equation because in a moment I will tell you what they're useful for. The sigma and the mu of the b-LOGNORMAL can be determined exactly in terms of the b, birth, d, death, and s, senility time. So you just give me 3 times, 3 instants in a person's life, or an animal's life, or a star life, and you can get mu and sigma. Now, you will excuse me, but here we are in Italy, and when I was a young student, you know, they stuck into my head the history of the Roman Empire. Oh my, sorry about that. So, you know, this is the part of history that I know best because I was a child. And so, as soon as I discovered that simple equation, I translated the history of Rome into an equation. And this is it. Rome was established in 753 BC, then peak, and finally death. And you see, please look at the moment. You see that the year 476, which is assumed as the collapse of the Roman Empire, Western Roman Empire, is obtained by the intersection of the tangent line in the decline to the timeline. Okay, so now finally we go to civilizations. So when I realized this trick, I took the liberty of writing down all the b-LOGNORMAL of 798, the civilization that came to my mind. But of course you could do it for any civilization. And in my opinion, we could do it for extraterrestrial civilization because I am a SETI scientist. The final goal of all this is not just justifying history as we know it. It was justify someone else's history. So, just look at this. Horizontal time, usual years. The red thing is the b-LOGNORMAL of classical Greece. The peak is Pericles, democracy, and all that. The violet thing is the Roman Empire. There are 1,000 years lost, which is the Middle Ages, where at least in Europe everybody was fighting against everybody. Then the green thing is the revival, Italian Renaissance. Sorry, for the pleasure of the Americans, the last and peakest thing, the red one, is the United States. Now, when I presented this in America, of course, they asked me, how do you know when the United States is going to end? Oh my, this is an embarrassing question, of course. But they tolerated me, and so there are 2 different answers. The number 1 answer is, well, you know, China is rising. So if China becomes the next biggest power, estimate roughly that around 2050, China might overcome. And someone said, oh, I thought that happened already. Okay. Anyway, these are just examples of civilization. Now, what you get out of this is that you can check the entropy differences. Now, please notice, the entropy differences, that is, the differences in the level of civilization. For instance, between the Spaniards and the Aztecs in 1519, when Cortes arrived in Mexico, and my calculation gives you 3.84 bits per individual. You have to keep into account the numbers of individuals in each of the 2 populations. So there were 20 million Aztecs against 20,000 Spaniards. And so on. The difference between a Victorian Briton and a Pericles Greek is 1.76. Clearly, this is less than the 3.84. And so on. So, conclusion of the story. This is my model that I called Evo-SETI, evolution and SETI. It's a mathematical theory. I am trying to write my last book about all that so that you can find all the papers in a single book. But the goal of all this is to prepare ourselves for contact with aliens. We have heard that there are a number of SETI searches going on. So, you know, it might happen. Let me just put it like this without any forecast. And if it does happen, my personal concern would be to find out how much more advanced than us those aliens are. And the hope is that this mathematical model can help in this regard. I would stop at this point, and okay, these are other things, but I skip, and I thank you very much for your attention. And okay, thank you very much. No, chair, please. You are the chair. Yes.
I wonder if you are aware of the Peter II, how you pronounce his name. In English, I put it as a Turkish because that's he is the biodynamics. Are you aware of his work?
No, sorry, Peter.
He studied the environment. Peter Turchin.
Oh, yes. Thank you. Not so much. I heard the name, but I didn't read the papers. What is that about? What?
He has used many mathematical formulas as a way of explaining different stages in the growth and decline of
Okay. Thank you.
If you had seen them, I would have been interested in your comments about them.
Thank you. I will have a look at that, please.
Yes, that's very interesting. I myself have a PhD in Greek and Roman history. I would say that most of my profession is not friendly to this kind of schematization of historical rises and falls. I find Turchin very interesting, don't get me wrong. I find this stuff quite interesting. The only center for this kind of very strict quantifying of this sort of thing, it would be at Stanford University, where you have people like Walter Scheidel, Ian Morris. Those two, for example, are quite friendly to big history and that sort of thing. They might find this interesting, but one of the dissatisfactions that I have with my field of Greek and Roman history is that it is so humanistic that this sort of thing, unfortunately, tends to get a rather negative reception. I guess I'm not asking you a question, I'm just wondering if you're aware of this.
Well, first of all, I thank you very much for the suggestion. Next time I'm going around Stanford, I will try to talk to him. It may not be easy, I know. But anyway, yes, you're right. And let me be more precise. This is precisely why I approach the big history community. Because at least the big history community acknowledges history. You know, this thing that I presented to you is halfway between mathematical stuff, whatever you like to call it, and history. History in the largest sense, from the Big Bang to now, including astrophysics. You know, I didn't mention all this, but you could apply the same equation to the life of stars. And guess what? This is important because the life of stars are millions or billions of years different from each other. So a civilization born around another star might be 1 million years, even 1 billion years ahead of us. We are just the young guys, so I would not consider civilization younger than us. So, conclusion, I thank you for the suggestion, and actually, I confess that I spent quite a few months organizing this conference, because here I could have an opportunity to present these ideas. Whereas in other conferences, this would not have been the case. Thank you. Yes?
One of the contentions with Stephen Hawking before he passed away was that human greed will be the downfall of at least Homo sapiens on Earth. And if you look at the common denominator in those civilizations that you put up, along with some of the writings of Jared Diamond, I can speak to that as well, is that one of the common denominators in these civilizations is greed when it comes to, you know, being in power, et cetera, et cetera.
Yeah.
Do you take that into consideration, and if so, how? Because it's difficult to put in terms of mathematics
Absolutely.
this type of cultural issue.
Absolutely. Okay, the answer is not yet, but not yet in the published part. But I've been trying hard. I don't know whether I failed or not. You know, you play with the equation, but to find the interpretation is the most difficult thing. So anyway, I've been trying to depict wars and especially battles in between two sides, playing with two b-LOGNORMALs. For instance, if you have two guys fighting against each other and one dies, clearly the b-LOGNORMAL of that guy goes very suddenly to 0. So if you translate that into mathematics, something has to come out. But I am not sure that I found all the equations. And so far I didn't publish that, also because I don't have the time, frankly speaking. Okay, I don't know if there are, yes, please, go ahead.
Thank you very much, Claudio. So you view 3.5 million years as the starting point of life. But we know that for a fact that at 4 billion years ago, sophisticated life environments were present. So would your results make any difference if you were to took 4 billion years as a starting point rather than 3.5 million years?
Thank you very much for touching this point. And my answer is absolutely clear. Let me speak as a physicist. The initial conditions, that is, whether we start at 3.5 or 4 or 3.8, as usually done in big history or whatever, has no importance. What matters are the equation, and the equations are the same. Of course, if you start with different times, you get different numbers. That is obvious. But this is a marginal condition. This is what physicists call the initial condition of the movement. Nothing more than that. What matters are the equation of the movement, not the initial condition. Okay? Yes?
If we get a signal from extraterrestrials, then how would this help to estimate how they are? What's your scenario for the
Well, thank you very much. This is another great question. I confess that I've been thinking about a lot. Now, this goes into, let me make an historical comparison, okay? Around the year 1501, Christopher Columbus was sailing around the coast of today's Nicaragua. And he was the first European to do so, okay? He was the first explorer from Europe to explore that coast. That was the 4th voyage of Columbus. Now, all of a sudden, the crew sighted a ship that was not a Spanish ship and was not either a barge like the Taínos or other primitive population had been sailing around that place. So by looking at the ship, Christopher Columbus inferred that that civilization were certainly more advanced than the Taínos, but not as advanced as the Spanish. Now, they were the, not the Aztecs, the Mayas. They were the Maya. It was a Maya ship filled with cacao or whatever that was moving around to sell the cacao. Now, let's translate that all the way into space flight. Now, here I didn't mention that, but today in the afternoon you will listen to a couple of talks by 2 Italian guys who work at the 64-meter radio telescope in Sardinia. And they will tell you, one of them in particular, will tell you about the KLT. What the hell is the KLT? The KLT is one name for a mathematical algorithm capable of filtering a very feeble signal out of noise of any kind. And here in Italy, we have been good at working for that. We have established a school and so on and so forth. So, making the comparison with Christopher Columbus, if we discover, the SETI guys discover a ship, spaceship of course, like Star Trek, moving around, for instance, from a stellar system to another stellar system, we may possibly infer from the speed of this movement how advanced those guys are. And this is the goal of my theory. I don't know whether I will succeed. Who knows? We start doing something. So, okay. Yes?
In my talk, I argue that biodiversity would
Exactly. Exactly.
But would you say that the relationships of life, like the symbioses that would occur with these species, would actually make the biodiversity even more, let's say, hyper-exponential?
Well, thank you again. This is another great question. Let me answer. I don't have the graph here, but let me tell you the answer. I published the papers that is trying to mix all I said today with one more thing that today I didn't mention. And this is the singularity. By singularity, scientists understand the time when computers will take over man. So in order to write this paper, which is again mathematical, I made one assumption, that the singularity is practically very close, as it was claimed, for instance, by Ray Kurzweil. I read his book. It's a great book, in my opinion. And he may not be wrong by too much, meaning 20 years, 50 years, 100 years, but sooner or later, I am honestly scared that computers will take over and nobody will be able to stop them. So suppose that the singularity is now. Now, translating that into mathematics, you draw a scene from you. This is the time. This is the exponential that I mentioned. But the exponential has a very peculiar property. There is only one point along the whole curve that has maximum curvature. And this is called the knee of the exponential. So I suppose that the exponential started 3.5 billion years ago or 4 billion years ago, when you please, with value 1, the first living species, RNA. And that I suppose that the knee is nowadays, or very close to nowadays. What do you get? I'll tell you. You get exactly an equation predicting that the number of species today should be around 100 million, which is not too far away from the 50 million that you mentioned. I can send you the papers, but honestly, I regard that as a step forward, because this mixes not only what I described in this talk, but also the singularity. Thank you very much.